Hello everyone, I am Wanderson. I am a chemical engineering student at the Federal University of Paraíba, and I would like to thank you for the opportunity of addressing you for the second CILAMCE and the third PANA CM on 2021. And today I'm going to talk about the modeling and simulation of an isothermal CO2 capture system using a hollow fiber membrane contactor. So it's necessary to introduce you some concepts, so I'm going to start by the CCS and the HFMC. CCS stands for Carbon Capture and Storage, and for this process we have some conventional methods such as absorption columns, but this process consumes a large amount of energy, so I'm going to introduce you a alternative method. So I'm going to talk about membrane gas absorption, and be more specifically, I'm going to talk about hollow fiber membrane contactors, or HFMC. HFMC are equipments that look like a heat exchanger, which has a shell and has a fluid leaking on the shell and has tube, but those tubes are made out of a selective membrane who electros pass just the solute. So we have also a fluid leaking inside the tubes. Then we have a mass transfer between these streams. So okay, let's talk about our system and the methodology used. Our system consists on two streams. The gaseous stream consists in a CO2 mixer who has water, nitrogen, and oxygen. Our liquid phase consists on an aqueous monoethanolamine solution, 30% in mass. We have counter current configuration, so we have the streams leaking on the opposite sides and opposite directions. We have the gas at the shell side of the system, and we have the liquid on the lumen side of the membranes. We got some considerations for the model. So first of all, we have the steady state, so our system have no variation on the time, and our model vary just with the axial coordinate, which means that our model is one-dimensional. To describe the behavior of the gas phase, we used an ideal behavior, so the gas varies with the concentration of CO2 and the pressure drop in an ideal way. We have a non-wetted model for the membranes, which means that there's no liquid inside the pores of the membrane. To describe the equilibrium at the interface, we use the Henry's law, so that interface is located on the internal surface of the membranes. And we have isothermal conditions, which means that the temperature remains constant on the entire process. To describe the mass transfer in our process, we use the concept of resistance in series. We have right here the overall mass transfer coefficient, and we have the summation of the local resistance on the process. So right here we have the resistance on the liquid phase, we have the mass transfer coefficient on the liquid film, we have the enhancement factor, which is describing the chemical reaction on the liquid phase. We have the resistance of the membrane, so we got here the mass transfer coefficient of the membrane, and we got here the resistance of the gas phase with the mass transfer coefficient on the gas phase. So Our chemical reaction is considered to be irreversible, bimolecular, and second order. So we have our expression where B is representing the monoethanolamine and A is representing the CO2. Here we have the product between both of them. Here we have the reaction rate where we have our kinetic constant and we have the concentration of CO2 and the monoethanolamine both on the liquid side. We got here some equations from the balance. So for the molar balance of CO2 on the gas phase, we have this equation, and we see that the CO2 is depending on the pressure drop and the mass transfer right here. We have on the second equation, we have the variation of the concentration of free air on the liquid phase. So this equation is from the stoichiometric of the reaction. We have right here our pressure drop described by a cosine type equation where we have kappa, which is the cosine constant, applied to an array of cylinders. As the results, we got some analyses, two analyses at least. First, we're gonna analyze the volumetric rate influence. So I vary the volumetric rate at the inlet side of the gas, and we see right here the behavior of the parameters of the process. So we have at the first, we have the capture ratio of CO2. So we see that when increase the volumetric rate at the inlet side, we have a decrease of the capture ratio. This is the concentration at the outlet side of the gas. So when we increase, we let more and more CO2 on the gas phase. This concentration starts to decrease due to the pressure drop, who start to increase when we increase the volumetric rate. We have a range of the volumetric rate to achieve a capture ratio greater than 80%. So this is the ideal range that we can use for this specific geometry of the system. The second analysis that I did is an analysis of the behavior of the HFMC with the axial coordinate z. So we got here the dimensionless axial coordinate. The z is our axial coordinate, and this big Z is the length of the HFMC. We have right here the local absorbed flux, so we have its profile, and we have the profile of the molar fraction of CO2 on the gas phase. We have right here the profile of the concentration of free air, which makes sense because we have a counting current configuration. So this is the rod profile, and this is the pressure drop of the gas. So seeing this, we can say that we have no pressure drop on the gas phase because it's minimal. So as the conclusion, we can say that the model follows the behavior predicted by the literature, and we solve the problem as an initial value problem. So we create a routine to fix the estimative at the point z equals 0 of the concentration of MEA. So we create a routine and we see that it fits very well. And we have two future works. We can introduce the energy balance to see how the temperature is varying with the process. So we got some references for our work, and I would like to thank you for your attention. You can find us at these email addresses, and bye bye.